Welcome to another deep dive. This time we're going to be looking at Jorgo Schneppat's essay, Quantenfelder und Teilchenphysik, ein Blick ins Mikrouniversum.
For our English-speaking listeners, that translates to quantum fields and particle physics, a glimpse into the microuniverse.
It sounds pretty complex.
It is a complex subject, but it's also incredibly fascinating.
Well, hopefully we can break it down a bit today and make it understandable and fun, too, for our listeners.
I think we can definitely do that. Schneppat does a great job of starting with a pretty familiar image. You know, the idea of tiny solid particles making up, well, everything.
Yeah, like little building blocks of the universe.
Exactly. But then he kind of throws a wrench in that picture.
He wants us to rethink that whole idea.
Yeah, he kind of blows it up, you know? He says, what if, instead of thinking of particles as these solid little things, we think of them more as disturbances?
Disturbances. Okay, I'm intrigued. Disturbances in what?
Disturbances in fields. So instead of imagining little billiard balls bouncing around, imagine a universe that's kind of like a vast invisible ocean.
Okay, I'm kind of visualizing that.
And the particles, they're like the waves that ripple across the surface of this ocean.
So not solid things, but kind of like energy patterns or something.
Yeah, exactly. And that something, that ocean, is what we call the quantum field. Just like we have the electromagnetic field everywhere, and light is a wave in that field, quantum field theory says that every single particle is an excitation of its corresponding field.
So there's an electron field and a proton field.
Exactly. An electron field, a quark field, a Higgs field, all of them constantly interacting. It's a whole universe of fields.
It's a lot to wrap your head around. But what does this field idea actually explain?
Well, it helps explain a lot of the really strange things that happen in the quantum world. Take the Heisenberg uncertainty principle, for example.
Oh, yeah. The idea that you can't know both the position and the momentum of a particle at the same time.
Exactly. You always have some uncertainty.
Like, the more you know about one, the less you know about the other.
Yeah. Exactly. And in quantum field theory, this fuzziness, this uncertainty comes about because particles aren't points. They're these disturbances spread out over the field.
Okay, I think I'm starting to get it.
It's a big shift.
It is. Now, Schneppat also talks about this concept of quantization. What exactly does that mean?
So quantization is one of the key concepts in all of quantum mechanics. It means that the energy in these fields, it's not continuous. It comes in these discrete packets. Yeah, we call them quanta. It's like a staircase. You can only step on specific steps. You can't step in between.
I like that analogy.
Yeah, it's a good one. And that means you can't have half a quantum of energy, for example.
So these fields are kind of grainy in a way.
Yeah, you could say that. And that graininess leads to all sorts of interesting effects.
Like what?
Well, for one thing, it means that particles can pop in and out of existence. They can be created and annihilated as long as the energy accounting all works out in the end.
Whoa! So these fields are kind of bubbling with potential particles.
That's one way to think about it. And that brings us to another really important distinction that Schneppat makes in his essay, and that's the difference between bosons and fermions.
Oh, yeah. He talks about how all particles fall into one of those two categories.
Right. And it all depends on this thing called spin.
Which is a bit more complicated than just a particle spinning around, right?
Definitely. It's an intrinsic property of the particle, kind of like their angular momentum, but it's more of a quantum mechanical concept than anything literally spinning.
Okay, so what's the big difference between these bosons and fermions? Why does it matter?
So bosons, they have whole number spins like 0, 1, 2, and they're kind of like the social butterflies of the particle world. They can all occupy the same quantum state. Meaning you can pack a bunch of them together in the same space, like photons, the particles of light. Think about how they bunch up to form a laser beam.
Oh, interesting.
Right, they're team players. Fermions, on the other hand, well, they have half-integer spins, like 12, 32, and they are fiercely independent. They absolutely refuse to share the same quantum state.
So they're like the opposite of bosons.
Exactly. And this is actually a really big deal. It's called the Pauli exclusion principle, and it's one of the most fundamental rules in quantum mechanics. It explains why electrons in an atom, for example, they arrange themselves in these specific shells or orbitals. Each electron is staking out its own unique energy level.
Wow, so the very structure of atoms is shaped by this difference between bosons and fermions.
Exactly. It's all thanks to this shift in perspective that Schneppat's encouraging us to make, thinking about the universe in terms of quantum fields instead of just particles.
It's pretty mind-blowing when you think about it.
It really is, and it has huge implications for how we understand the universe at its most fundamental level. And it's amazing to consider how this idea of these quantum fields and the particles that come from them, like how this has just totally revolutionized our understanding of physics.
Yeah, it's hard to imagine physics without it now, you know?
Absolutely. Schnippat takes us through a little bit of the history, how we got here. And it's really a story full of these incredible insights, these huge leaps of imagination.
Yeah, he mentions a lot of familiar names, like Max Planck, right? Where does he fit into all this?
Well, Planck was working back in the early 1900s, and he was trying to understand this problem of black body radiation.
Which is?
It's like how hot objects emit light. And classical physics, just the physics of the time, it just couldn't explain the patterns they were seeing.
So they were kind of stuck.
Totally stuck. And that's where Planck's big idea comes in. He proposed that the energy of light, it couldn't just take on any value. It could only exist in these, discrete packets.
Kind of like those quantas you were talking about before.
Exactly. He called them quanta, and this idea, this quantization of energy, it was like a bomb going off in physics.
It was a huge shift in how people were thinking.
It really was. And then Einstein comes along.
Of course, science.
And he took that idea and he ran with it. Einstein being Einstein, he thought, well, if energy is quantized, then maybe light itself is made up of these quantized packets.
And those packets are?
Photons. Boom. The concept of light as both a wave and a particle was born.
A wave and a particle.
That's the quantum world for you, always keeping us on our toes.
It's incredible how far that one idea has come. But, it didn't stop with Planck and Einstein, did it?
Yeah.
There were other people who contributed to all this.
Oh, tons. Niels Bohr, Werner Heisenberg, Erwin Schrödinger, all these giants of physics, they were all wrestling with this stuff, trying to come up with new theories, new mathematical tools to describe this weird quantum world.
Schnippat gets into a little bit of the math, but I think maybe we can spare our listeners the equations.
Yeah, maybe. But there are definitely some key takeaways here without getting too deep into the weeds.
What are some of the core ideas behind the math, just conceptually?
Well, one of the really important concepts is the idea of a Lagrangian.
The Lagrangian.
It's essentially a mathematical function that describes the energy of a system. In quantum field theory, we use it to, write down the equations of motion for the fields, how they change and interact over time.
Okay, so it's a way to, model how these fields behave, even though they're operating on such a tiny scale.
Exactly. And these mathematical models have led to some incredibly precise predictions.
And they've been confirmed by experiments.
Oh, yeah. Again and again. And probably the most famous tool that came out of all this, it's the Feynman diagram.
The diagrams with all the little squiggles and lines.
Yes. Richard Feynman, this brilliant physicist, he came up with them as a way to kind of visualize these complex particle interactions.
They're so simple looking, but I know they represent something super complicated.
Oh, yeah. Each line and each vertex in a Feynman diagram, it corresponds to a very specific mathematical term in the equation. They're like a shorthand.
So instead of wading through pages of math, you can just look at these diagrams and kind of see what's happening.
That's the idea. It's a powerful way to visualize and calculate the probabilities of different outcomes, when particles collide or interact.
Okay, so Feynman diagrams, Lagrangians, it's all starting to come together.
Yeah.
Now, Schnippat highlights some specific examples of quantum field theories. He talks about quantum electrodynamics, or QED, as one of the most successful theories we have.
It is. QED describes how light and matter interact. Specifically, it deals with charged particles, like electrons.
So it's like the theory of electromagnetism, but at the quantum level.
You got it. It explains so much, like how atoms emit and absorb light, how magnetic fields behave. It even predicted antimatter.
Antimatter, like the stuff in Star Trek.
Exactly. It's like matter, but with the opposite charge. So an anti-electron, which we call a positron, it has a positive charge instead of negative. And QED predicted these particles before they were even discovered.
Wow. Okay, so QED is a pretty big deal. But then there's the strong force, right? Schnippat talks about that one too.
Oh, yeah, the strong force.
Yeah.
And that's where things get even weirder.
Yes.
Well, the strong force, as you might guess, it's incredibly strong. It's what holds the nucleus of an atom together. All those protons and neutrons packed in there.
Right. So it's got to be strong to overcome the repulsion of all those positively charged protons.
Exactly. And the theory that describes the strong force, it's called quantum chromodynamics. QCD for short.
QCD. Got it. What makes it so weird?
Well, for starters, it introduces a new type of charge, something called color charge.
Color charge. Wait, so are quarks literally red, green, and blue?
No, not literally. It's just an analogy. Like how electric charge has two polarities, positive and negative, QCD says that quarks have three different types of color charge, red, green, and blue.
Okay. But instead of attracting or repelling, these colors have to combine in a specific way to, neutralize the strong force.
Exactly. You can't have a lonely red quark just hanging out by itself. It'll always be bound to other quarks in a way that cancels out the color.
So, a proton has to have one red, one green, and one blue quark to be stable.
Yep. And we call this color confinement. It's one of the defining features of QCD, and it explains why we never see free quarks just floating around. They're always bound together in these color-neutral combinations.
So it's like a cosmic color puzzle.
Kind of, and it's just another example of how this shift in perspective, from particles to fields leads to these really interesting and kind of mind-bending ideas.
It's definitely a whole different way of looking at the universe.
It is, and it's just the tip of the iceberg.
It really makes you wonder what else is out there, what other connections we might discover.
Definitely. And this actually leads us to the standard model of particle physics. It kind of brings together all those forces and particles we've been talking about.
Schneeplatt talks about it as being super successful, but he also points out that it's not a complete picture.
Yeah, the standard model is great. It's a huge triumph of modern physics. But it's not the final word. There's still a lot we don't know.
Like what? What's missing?
Well, for one, it doesn't include gravity.
Gravity.
Yeah, it's kind of the odd one out.
It seems like gravity is always causing trouble when we try to fit it in with the quantum world.
It's one of the biggest mysteries in physics, How do we reconcile gravity, which works on these huge scales, with quantum mechanics, which governs the tiny world of particles? We haven't figured it out yet.
And the standard model also doesn't account for things like dark matter and dark energy, right?
Right. Those are two of the biggest mysteries in cosmology. We know they exist.
Because of their effects on galaxies and stuff.
Exactly, because of their gravity. But we have absolutely no idea what they are.
It's kind of humbling, to realize how much we still don't know.
It is. But it's also exciting. It means there's still so much to discover.
So what are some of the theories that try to go beyond the standard model? Schneeplatt mentions a few, like supersymmetry.
Supersymmetry, yeah. SUSY for short. It's a really interesting idea.
What's the basic idea behind it?
Basically, it proposes that for every known particle, there's a partner particle, a supersymmetric partner. So for the electron, you'd have a selectron. For a quark, you'd have a squark.
It sounds like something out of a science fiction movie.
It does. But the cool thing is, supersymmetry could potentially solve some problems with the standard model.
Like what?
Well, for example, it could explain why the Higgs boson has the mass that it does. Because the standard model on its own has some trouble explaining that.
And the Higgs boson was a big deal, right? That's a huge discovery.
Oh yeah, huge. It was one of the biggest confirmations of the standard model. Because the Higgs boson is associated with the Higgs field, which is what gives other particles their mass.
So it's like the mass giver.
In a way, yeah. It's been described as like a cosmic molasses that permeates the universe, and particles, they have to kind of wade through it, and the more they interact with the Higgs field, the more massive they become.
Okay, I think I get it. So supersymmetry could help explain some of these things that the standard model struggles with.
Potentially, yeah. But there's also string theory, which is even more out there.
String theory. That would always sound super complicated.
It is. It's a pretty radical idea. Basically, string theory suggests that the fundamental building blocks of the universe, they're not particles, they're these tiny vibrating strings.
Yeah.
And the different vibrations of these strings, those correspond to different particles and different forces.
It's almost too weird to imagine.
It's definitely mind-bending. And it's also very hard to test experimentally, So it's still a very theoretical idea. But it has the potential to, completely revolutionize our understanding of physics if it turns out to be true.
It's incredible to think about all these ideas. But Schneeplatt also emphasizes how important experiments are, right? It's not just about coming up with theories, it's about testing them.
Absolutely. Experiments are how we know if we're on the right track. They can confirm our theories, or they can completely blow them out of the water. And sometimes they even lead to completely new discoveries that we never even thought of before.
He mentions the Large Hadron Collider as a prime example.
Oh, yeah. The LHC is an incredible machine. It's the most powerful particle accelerator ever built.
They basically smash atoms together, right? At super high speeds.
Protons, actually. They smash protons together at nearly the speed of light. And by looking at the debris from those collisions, we can learn so much about the fundamental nature of matter.
It's like our best tool for looking into the heart of matter.
It really is. And it's constantly pushing the boundaries of what we know about the universe.
It seems like there's still so much to learn about quantum fields and particle physics. And so many directions for future research.
Oh, absolutely. It's a field that's constantly evolving, you know. New discoveries are being made all the time, and our understanding of the universe is getting deeper and deeper.
What has stood out to you most from our look at Schneppat's work?
You know, for me, it's this constant interplay between theory and experiment. We have these incredible theorists coming up with these mind-blowing ideas, and then we have equally brilliant experimentalists who are designing these incredible experiments to test those ideas.
And that push and pull between those two sides, that's really how science progresses.
Exactly. It's this beautiful cycle of discovery. Theories lead to experiments, and then the results of those experiments can either confirm the theories or lead to new ones.
Well, I think Jorgo Schneppat has definitely given us a lot to think about. His essay offers a fascinating glimpse into this world of quantum fields and particle physics, this world of the very small and the very big, the known and the unknown.
It's a world that's full of wonder and beauty and endless possibilities for exploration.
And that's what makes science so exciting, this constant journey of discovery. There's always something new to learn, always another mystery to unravel. So keep those questions coming, keep exploring, and join us next time for another deep dive into the fascinating world of science. We'll see you then.